Hello, you all. I'm back going to do some more linear algebra preparing for my exam later today. And we shall continue with some problems from section 1 through 4 of the textbook Linear Algebra Inter a Geometric Approach. So perhaps I'll go back to section 1.1 and start working through again. And be sure to like if you haven't, subscribe if you haven't. Join my Discord. We can talk about science and math and all of those good things. And let's go to the textbook and see what we'll cover. So back to section 1.1, vectors, and let us try the 20s. All right. So proofy type stuff. I hate proofy type stuff, but gotta do it. 1.1. So we on number 20. So we're assuming that U and V are parallel to each other. And they're in Rn. So we want to prove that span UV is a line. So basically span of two vectors means that it's all spaces covered by linear combinations of U and V. Now, since U and V are parallel, we can say U is parallel to V. That means they're going in the same direction. So for instance, utilizing our previous idea of U dot V, and let's say that's equals U dot the V that's parallel to U plus the V that's perpendicular to U. So that equals the U dot V parallel plus U dot V perpendicular. And of course, if they're perpendicular to each other, the dot product equals 0. And we know that the parallel to each other is U dot alpha U. So that equals alpha U dot U, or alpha, the magnitude of U squared. So we know that they're going in the same direction in that case, but since they're parallel, V equals V parallel to U. Since they are parallel, V equals that. So that means that U dot V also equals the scalar times the magnitude of U squared. So, and since V equals parallel to U, that means that V equals some scalar of U. So that means that U plus some scalar of U equals 2 scalar U, which is still a line, which is the same line just scaled And you can sort of absorb the 2 alpha into one scalar. So we know that u plus v equals some scalar of u, or vice versa. U plus v is some scalar of v. Thus, u plus v is some scalar u, which is a line. Because if you have any vector and you scale that vector, so if I have vector u, and then I scale that vector, I just end up with a line along that vector. So I think that proves that. And let me take a look and see what I have for my original answer. Yeah, that's good enough. It looks like in my original proof, I also wrote them going in the same direction, which means that u plus v is double the length of those in the same direction, which is still a line because they're parallel. So it's good to have an illustration as well. Um, and why don't we do something different? Did I have to do 23? Let me see. I did, and it looks interesting. So let's do 23 of the same section. So it says, instead of the line, L equals X, or L is X equals XO plus RV. And R is a real number. And the plane P is going to be X equals SU plus TV. And we could assume that these V's are the same since they're both named the same, those vectors. So it wants us to show that if L intersects P, that X naught is in P. Okay, so if we look at this, we'll draw each of these. We have a line with an X naught. First, we have our X naught. And we can say this is X naught, which is some line coming from the origin. And then the line that we're dealing with is certain scalars of that. So that'll be X naught. And this will be X naught plus RV. So this vector in this direction is the direction V, and it's scaled by aura up and down to make that line. And I should be able to find that in the book somewhere. Let's see, I remember seeing that image. There it is right here. It looks like I noted it incorrectly. I mean, that is technically XO plus RV, but it seems like the book likes to write it on the other slant. So looking at the book here, this is basically what I was drawing right here. Oops. So let me expand this. Got that. So you see XO, it's the left arrow. They call this point T, where XO lands. You can also call it XO. And TV is going in that direction, so I have that right. So XO plus TV ends up being this point, or XO plus RV. They used, we have our scale as R. And this right here, in this example, this section here would be RV. Right, so XO plus RV. So it is right, it's just the book. I guess I always have a sort of love-hate relationship with the notation of books. And as we scale RV, XO plus RV will basically scale along this line up and down this blue line to make all the uh, uh, vectors that span that line. Now, what they're also saying is that there's a plane actually, and that line is in this plane, that blue line, and they want us to show that X naught must be in that plane if the line intersects that plane. And it doesn't even have to be parallel to it. It just needs to go through it at some point, such that that line, that point on that line goes through the plane. Let's take a look at that. So the little scroll button is right there by the problem button. This makes for some problematic scrolling sometimes. Oh, there it is again. We just fit this to the window, right? So XO, which is P in the example we just looked at, this point has to be on the plane. And this plane can be angled either way. This plane could be angled up, this plane could be angled down, it could be angled in either direction. But wherever it's facing, this point has to stay on that plane. So you could almost say that this point becomes the fulcrum of the plane if XO and that line intersect. Now, one thing that find interesting is well, I see. The reason why I was about to point out the fact that this plane could be facing any direction, therefore it could intersect the line, let's say here, and the plane is not intersecting at P, but the line is still interconnecting P. But the detail is that these vectors are the same. So the fact that wherever the plane is, one of the vectors that make the plane goes along this line, and assuming that the plane is infinite, it scales every single point of this line. It has to also scale uh, every point along this line as well because they're the same vector. So that line would actually be on the plane because they're going in the same direction. So basically, you can say that the u vector will be in the plane, making a right angle or some kind of angle with v, not necessarily a right angle. So I'll put it here. But both of the highlighted in yellow are in the plane because v is in the plane and they're going in the same direction, even if it's offset. And that means that since XO is a part of that line, XO has to be in that plane. So what we can say is, in order for them to intersect, at some point, XO plus RV equals SU plus TV. You can see how they both have an X, so it's almost like a hint. But since they intersect, at some point, the line and the plane has to meet. That's always the case. So I can say XO equals SU plus TV minus RV. And thus we can say SU plus T minus RV. And I can subsume whatever that constant is into B. Thus, XO is in the plane because every single scalar of B is in the plane because the plane is spanned by U and V. So you can say L is also BV, given that B is T minus R. Let's see what I showed for the original one. Oh, so I need to start watching live so y'all can let me know when my paper isn't showing. But that's what I was drawing right there. So let's take a look and see what I have. So what I think I'm going to do, since I've already reviewed some problems, I think I'm going to review some concepts. And looking at 23, that is what I did, and I explained everything. right? So give me a moment. I'll stop the stream. Then I will start a new stream just talking about some of the concepts we went over so far in the linear algebra geometric approach.